Hi, and welcome back. You might recognize our next speaker from the LA chapter of Django Girls, a nonprofit that inspires women who are interested in tech. She's a self-taught software engineer and is here today to teach us a little bit about deep learning on computers small enough to fit inside your pocket. Please welcome to the Hackaday Supercon stage, Leigh Johnson.
Hello, everybody. Can you hear me in the back? Cool, awesome. Hi, I'm Leigh Johnson, and I'm the founder of a startup that automatically matches students with unclaimed scholarship money. I also run a consulting firm that specializes in shipping MVPs for seed stage startups and Series A startups and beyond. Capital is so easy to get these days that a lot of companies find that technical strategy is where their dearth is, and execution that's required to bring products to market is missing. So I help bridge that gap. And today I'm going to be talking to you about how one of my buddies who does a lot of work in emerging markets, he asked me if I could build a computer vision device that worked offline and could cost less than about $100 per unit. So raise your hands if you've ever done a Raspberry Pi project. Yeah, a lot of people in this audience. Cool. Now raise your hands if you've ever done any work with machine learning. Sweet, a lot of people too. Awesome. So real quick, I'm going to do some term recap just to catch everyone up to speed. So what I mean when I say portable object detection is I want to be able to point my Raspberry Pi camera at something and get a prediction about what that thing might be. And some real-world examples of this are a device that can identify plants, or an assistive device to help someone who's vision impaired, or a cheap way to build computer vision for an autonomous self-driving robot. And if you are hearing impaired, I have some of my speaker notes online at rpi.leejohnson.me. You can follow along. I might deviate or ad-lib a little, but I myself have an auditory processing disorder, so if you want to read along, there you go. You can tweet at me too at greplee. And I have the code that I'm developing online at GitHub at RPI Vision. So pull that down, check it out. I'm trying to build a platform that I wish had existed when I got started. So real quick, I'm going to, looks like we've got a technical snafu. Okay, I won't show you any video. So here's the hardware essentials that I'm using. It's really simple. This isn't an auto AI kit. This is just a Raspberry Pi 3, a Pi Camera V2, and a 3.5-inch TFT. And some more term definition. What is machine learning? It's just pattern recognition, automated pattern recognition, fundamentally. And no data scientists are here to throw fruit at me for simplifying it that much. So I'm going to proceed. And what is a neural network? It's optimization of machine learning pattern recognition. So a lot of the hard part about tuning a machine learning model is tuning hyperparameters. And what a neural network brings to the table is some automated optimization as well. So what's TensorFlow? What is Keras? TensorFlow is a really cool framework developed by the Google AI organization. And Keras is a higher level framework that aims to simplify software interfaces that train, analyze, and save machine learning models. TensorFlow is just one of 3 supported backends by Keras. So you can bring in other backgrounds like Cyanos or Microsoft CNTK. That means that you can experiment very easily with other backends. Keras also provides a solid tool chain for data preprocessing. So that means if you use Keras, you can easily port your data and your prediction pipeline over to a different backend for easier experimentation. Okay, so really basic. Let's go through what a convolutional neural network is. And there are I'll say that there are a lot of types of neural networks. Today I'm just going to be talking about this one, CNN. And I'm going to talk about how they work at a very high level. So you start with an input feature map, which you can see on the top right there. It's got an input depth, width, and height. And a convolution works by sliding this 3x3 window, those 3x3 input patches, over the 3D input mat, stopping at each possible location. And then each 3D patch is then transformed into a 1D vector with the length determined by your output depth. And the transformation occurs via a tensor product, or a dot product if you're a mathy calculus person in the audience. And that is informed by a learn weight matrix, also called a convolutional kernel. You'll see that term a lot too. So then those vectors are reassembled into another 3D output map at the very bottom. And what's really cool is every spatial location in the output feature map corresponds to the same location in the input feature map. So the lower left-hand corner of that output feature map corresponds to the lower left-hand corner of that input feature map. Okay, that was kind of a lot, right? So what are CNNs good at? Why would you use them? Why would you use them in one of your Raspberry Pi projects? They're really, really good at learning spatial hierarchies of patterns. So what does that mean? How do they do that? The first convolutional layer in a CNN will learn small local patterns, local minima, local maxima, like edges. And the second convolution layer will learn larger patterns. And then after that, and so on, building into an increasingly complex spatial pattern that can recognize more complex visual concepts. Some other cool properties are that CNNs are translation invariant. That means that after learning a pattern in the lower right-hand corner of a picture, the ConvNet can recognize it anywhere, like in the upper left-hand corner. So really cool for image processing and recognition. A more densely connected network would have to learn those patterns over and over again. So it would have to learn that an upside-down cat is also a cat, or a right-side-up cat is also a cat, or any configuration possible of a cat is still a cat. And this image really helped me grok what the pieces, like the local minima and maxima, were actually targeting when you're trying to identify a cat. So if you're trying to figure out what is it that makes up a cat, you can see that these edge boundaries are starting to add up to increasingly more complex features, which add up to a cat. These are also from a great book called Deep Learning with Python, which you should totally check out if you're interested in this. Okay, so I talked about building a software platform. I wanted to put TensorFlow on a Raspberry Pi, and there didn't exist a lot of tooling to get started with training my models and productionizing on the Raspberry Pi. So I created the interfaces that I wish had existed, where I can basically run this trainer task. And you can choose to run it locally. I would recommend not running it on the Pi. Run it on some machine that has GPU acceleration, unless you've just got a lot of time to kill or a very small data set. And you can also run it via Google Cloud ML Engine through a script that I wrote. And if you can check that out, and I've got instructions about how to set up Google Cloud Platform. I would definitely recommend running it in the cloud, just because it's a lot easier to monitor and maintain. I created a sample task based on this dice training set. So if you check out some of these images that I took, I am trying to train a model not only to recognize the shape of a dice, like a D20, a D4, a D6, but also what face is facing up. What face should I read on the dice? It's a pretty straightforward task if you've never done anything like this before, so here's a good starter. All right, so let me talk a little bit about the software architecture. So here's my detector, and this is what's running on the Raspberry Pi. So I wanted to create an interface where I could just pass in the name of a model, instantiate it, and be ready to go. And I'll talk to you a little bit about how this is actually working. So first, we're going to, in one process, load up a model. Here we're using MobileNet v2. MobileNet v2 is a pre-trained convolutional network. And so what that means is it's trained and benchmarked against the ImageNet dataset, and it's a general purpose object detection model, which is really well suited for small devices, hence the name MobileNet. And you can read a little bit more about it on Google's AI blog. And so in the software architecture, I don't want to be buffering frames from my Raspberry Pi in the same process. I want to, start a new, or in anything in the same thread. I want to start a new thread and read that frame buffer through an async process, or I want to be able to pull that out whenever I want to, and then make a batch prediction against that frame buffer. And then optionally, I can render a bounding box overlay over that. I've also included instructions about how to set up frame buffer copy in this repo. Frame buffer copy is something that can, as the name might indicate, copy frame buffer. And here I'm copying frame buffer from HDMI to my SPI, which is the TFT screen's display output. Okay, this is a video that's not going to work. All right, so here's a little bit more about Tensorboard visualizations. And so the thing I really wanted to do here was make sure that I prioritize versioning and analytics here, because it's important to create reducible scenarios and keep track of incremental changes when you're doing science. I created some custom callbacks for Keras model training and also patched Keras's preprocessing library in order to give us the option of saving Tensorboard events and model checkpoints directly to Google Cloud Storage. Tensorboard is what you see on the right. That's showing me kind of the tail end of my dice training model. You can see the dense output layers. You can see the final activation. You can see the intermediary ReLU activation there. I'll be writing a proposal and pull request to get those features incorporated upstream in the next couple of weeks. And I've open sourced the Raspberry Pi Vision bucket. So my training data is available to the general public, in particular the dice data that I've taken pictures of is open to the general public now. So what I wanted to get people started with was the ability, one, to download and use a pre-trained network straight out of the box. You can do that. I also want you to be able to take a pre-trained network, use only what's called the convolutional base, and then train your own network on top of that. And this is a fairly processor inexpensive cost. You can do this on the Raspberry Pi. And then 3, I want you to be able to train your own convolutional base by yourself. This is what you would need a GPU accelerated machine for. Here's an example of mine with versioning. If you want to check out some data sets, like if you're not sure what data sets to get started with, this is a really good data set tool. So if you're eager and bursting to go out and find some data, train your own neural network, try this first. And thank you. If you want to contribute to this project at all in the form of user case studies, I'm trying to figure out, okay, if you have a Raspberry Pi, what do you want to do with it if you're using computer vision? Please feel free to open an issue. My goal here is to develop a framework for training CNN models and productionizing them on a Raspberry Pi. So if you're interested in that at all and collecting examples of what people want to do and building a framework that'll capture all of those usages. Some of the next practical applications include diagnosing skin cancer in humans. This is what my buddy originally came to me to try to do, using a small $100 device that we can go ship off to India. And I'll be doing some more development and testing by building a model of healthy and unhealthy dog poop, which is why I've got my corgi there in the frame. And then I'll be open sourcing that data set as well. I do need to gather data, so if you want to send me photos of dog poop, I consent. If any of this sounds interesting, the dog poop, the computer vision on a Raspberry Pi, follow me on Twitter or check out this repo and open an issue with your comments. Thank you.
Thank you.